Hello, everyone. Apparently, I start them all with hello, everyone. So I need to come up with a new catchphrase like, I don't know, hey, how's everybody doing? Or I don't know, something random like that. Anyway, today we're going to talk about the natural logarithm and base e. So most of you think that e is a vowel. Now we're going to talk about e as a number. So to start things off, first thing we're going to do is we have this expression 1 plus 1 over n to the n. And what I want you to do is I want you to plug in the number 1. So when you plug in the number 1, you get 1 plus 1 over 1 to the 1. That's 1 plus 1 is 2 to the first is 2. All right. Now I want you to do it again, only this time I want you to plug in 10. So we have 1 plus 1 over 10 to the 10th power. Now, you're going to need some calculator help pretty quickly. But that's going to be 1.1 to the 10th power, which is going to give us 2.59374, blah, blah, blah. All right. Now, I want you to do this over and over and over again for 100, 1,000, 10,000, 100,000, and 1 million. And go ahead and calculate those numbers. Okay, so we've calculated all those numbers. Hopefully you paused it. And what do we notice? We notice we started off with a 2, then we had a 2.59, then we had a 2.70, then it became 2.71, then it was still 2.71, only now it's 2.718. Then it was a 1 after, and now it's a 2.712, then it's a 2.7182, and then we didn't change until we got to the 8. So what's going on here is we are looking at a limit. This here is some notation that you will see when you take pre-calculus. We are looking at the limit as n approaches infinity. So as n gets really, really, really big, so we did up to 1,000,000, what happens when it's 10 million, 100 million, a billion, and so on? What is this number going to get to? Well, it's going to get to 2.71828, blah, 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 blah. Okay, kind of like we see here with the million. And then we're not going to see a change when we do 10 million until that zero will be the number that changed. So when we look at this limit, we're saying what happens to this value, this 1 plus 1 over n to the n, as n gets really, really, really big? And the answer is that it is equal to this new number that we call e. E is the natural base. So we will have, it will act like a regular base, like a 2 to the x. We can now have an e to the x. And it can act as a base in a log instead of like a log base 2. We can have a log base e. Similar to pi and numbers like the square root of 2, the number e, so I know we're used to thinking of it as a vowel, but the number e is an irrational number. The value of E is approximately 2.71828, blah, blah, blah. It is referred to as the natural base. And an exponential function with a base E is called a natural base exponential function. So E is no longer a vowel, it is now a number. So when someone asks you what's your favorite number, you can now say E, and they'll look at you very strangely. Okay, so what is this E thing all about? Key concept. The function f of x equals E is used to model continuous exponential growth. The exponent, notice, was a positive x, so we have exponential growth. If we have e to the negative x, it's used to model decay. Notice there, the exponent is a negative number. The inverse of a natural base exponential function is called a natural logarithm. There's a lot of nature going around. This logarithm can be written as log base e of x, but because we use it so often, kind of like log base 10 is the common log. We just say log. We don't say the base 10 anymore. Instead of writing log base e, because again, it's used so often, we write it as natural log. We say ln. ln, think in like foreign languages, how the descriptive word is after. So this is like logarithm natural in Spanish or something, or maybe French, I don't know. But it's abbreviated ln, logarithm natural. The graph of e to the x here is 2.718 to the x. So it's in between a 2 to the x and a 3 to the x. If we look at the natural log of x, sorry about that. If we look at the natural log of x, it's going to be that red graph there, y equals natural log of x. And if we drew in the y equals x line, you can see that the blue and the red curves, if we fold it along that green line, will match perfectly because they are inverses. All right, so how are we going to use this newfound e number? We can write the equivalent base e exponential function for a natural logarithmic equation by using the fact that the natural log of x is really just log base e of x. So if we look at the natural log of 4 equal to x, we could rewrite that as the natural log, log base e of x. Start over. The natural log of 4 equals x. We could rewrite that as log base e, because log base e really means natural log of 4 is equal to x. And then what? Then we could rewrite that whole thing. We can rewrite this as an exponential, and we will get e to the x equals 4. So the natural log of 4 equals x, and e to the x equals 4. That is the log rewritten as the exponent, and the exponential rewritten as the log. So we can go back and forth between the two. So here we have e to the x equals 5, and we want to write that in logarithmic form. So that would be log base e of 5 equals x. But instead of writing log base e, we now write natural log of 5 equal to x. If we look at number 8, we have e to the 8th equals x. Rewriting that, we would say log base e of x equals 8. But again, we don't say log base e anymore. We would say the natural log of x is equal to 8. We can also take a log and rewrite it as an exponential. We have natural log of x equals 1.2528. So there's really log base e of x equals 1.2528. What are we going to do? We're going to rewrite this as an exponential. We're going to pop it. That'll give us e to the 1.2528 equals x. Again, next one we have the natural log of 25 equals x. So we can think that this is really log base e down here. Rewrite it as an exponential. Pop it. That gives us e to the x equals 25. So the way we rewrite logs with any base 2, 4, 10, 1/2, something like that, we can also rewrite log base e the exact same way. Exact same rules. Nothing changes there. We just have this new number that's in between 2 and 3. Simplifying expressions. So yesterday we learned, or no, not yesterday, actually today, but it's a couple days from now for you watching this video at home. We learned about expanding and condensing logs. Same rules apply with natural logs. Nothing is different. So what do? We've got this 4 out front. We want to condense this into a single log. Condense, or the more technical term, smush. it back together. So we've got that coefficient of a 4. Where does it really belong? It came from the exponent, so we're going to push it back up top. So now we have the natural log of 3 to the 4th plus the natural log of 6. Then what? I still have 2 logs. My goal is to get a single log. So what do? We've got addition. How do we put addition back together? We put it back together with multiplication. So we will have only 1 log now, and then we will have 3 to the 4th times 6. What is 3 to the 4th? 3 to the 4th is 81 times 6 is 486. So this will be the natural log of 486. Again, in the end, we want a single log, just 1 log. All right, let's look at number B. Not really number B. All right, so again, we've got a coefficient out front. Where does that belong? It came from the exponent. So that gives us the natural log of 3 to the 2nd plus the natural log of 4 minus the natural log of y. So we've got some addition here. So what do we do with addition? Where did it come from? It came from multiplication. So now we'll have the natural log of 3 squared, I'm going to say 9, times 4 minus the natural log of y. Then what? Well, now we've got subtraction. Where did subtraction come from? Subtraction came from division. So we will divide now, again, taking the 2 logs, combining them into 1. We'll have the natural log of 9 times 4 is 36, divided by y. Again, log base 2, log base e, also known as the natural log. The rules are the same. Nothing has changed. Note, because the natural base and the natural log are inverse functions, they can be used to undo or eliminate each other. So just like before when we had log functions, we would rewrite them as exponentials. We can take an exponential and rewrite it as a log to solve the problem. So here we have 3 times e to the negative 2x plus 4 equals 10. First thing we want to do is we want to isolate the exponent, the exponential part. So we're going to need to subtract 4 from both sides. That gives us 3e to the negative 2x equals 6. We need to divide both sides by 3. E to the negative 2x equals 2. Now we're ready to rewrite it. Now we're going to rewrite this as a log. This would be log base e, natural log, of 2 equals the negative 2x. Then what? Get x by itself, divide both sides by negative 2. So x equals, now if you take a look at your calculator, you'll notice you have an ln button. It's usually right under the log button. So what you can do is you can hit the ln of 2, close your parenthesis just like you would have to do with the log, divide that by negative 2, and you get negative 0.3465, blah, blah, blah. I didn't tell you where to round it to, so let's round it to the nearest hundredth. So x then is equal to negative 0.35. Okay, so again, we have a log button on our calculator. Next one, we need to get that log by itself this time, so we're going to divide both sides by 2. That gives us the natural log of 5x equals 3. Now, this is a log, so we're going to rewrite it as an exponential. Remember, there's a base of e down there. So we're going to take that e over, pop the 3 up. So e to the 3rd equals 5x. Divide both sides by 5. X equals. Notice your second ln button is really an e to the x button. So if you hit second, the natural log button, it gives you an e with the exponent already there. Type in your 3, close your parentheses, divide that by 5, and we get x equals 4.017. So that'll be 4.02. I want you to take a look at the next one. There's a little e down there. We're going to run out of time. So I'm going to finish it, and you guys can check your answer. You guys try it real quick. Okay, so when you rewrite it, you get e to the 36th minus 4. E to the 36 is a ridiculously big number. It goes in scientific notation, 4.31 times 10 to the 15th. Crazy number. Probably won't give you any like that later. All right, peace out. Have a good night, and do your homework. Thanks, guys. Bye.